speaker for the final lecture.
Yes. It was an expensive one. How much transfer did you pay?
Actually, he paid us, but he's wearing the wrong jersey because he's really the keeper. But never mind. Our very own Ronaldo Abramsky.
Right. Thank you very much, Mike. Indeed, we've come to the the end of my series of lectures, and the end of this workshop, which I've really enjoyed enormously, I must say. As I mentioned, this is going to be about some very recent work, and I thought it would be a nice way to finish as the road goes ever on. So this is in fact very recent work, a visit to Amsterdam where I had some nice discussions with Yoko Farmerman. So it concerns a topic that's a bit different from other things we've seen in this workshop, but yet still related, I think, as I'll try and explain. So let me begin with ideas about dependence, independence, and how they are another aspect of this very rich subject of information flow. So if we begin with something very familiar, like a definition of epsilon delta definition of continuity, and as this is often portrayed as a game, we're trying to show that the function is continuous. We're challenged with an epsilon, we have to produce a delta, such that if we confine the input or confine our possible inputs around the given x as close as delta, that will be within epsilon of the outcome. And as we know, we have the notion of uniform continuity. So a place where students really confront quantifiers and the subtle differences about quantifiers is in such things as distinction between continuity and uniform continuity, or pointwise and uniform convergence. So with uniform continuity, we reorder the quantifiers and we see that the delta can still depend on the epsilon, of course, but must be chosen independently of the x. So we have an idea of what depends on what when we have these quantifiers. And putting an existential in the scope of a universal means that we think of some kind of choice, we think of a kind of game where between two players for choosing the values of the variables bound by the quantifiers, and as we move the existential outside the scope of the for all x, the choice becomes independent of the choice of x. And this can of course be formalized as a suitable sort of game, but that isn't going to be the key issue in this talk. And there are actually many examples. Clifford Hodges quotes us some nice examples from Serge Lang in his books on number theory, where certain theorems are stated saying that you have some parameters and that you can then find a bound in some estimate, where he states explicitly that this bound that you find depends on certain of the parameters and does not depend on some others. And that can obviously be very important to the strength of the result. So that's an important issue in stating any such results. And if we think back in the quantum realm, it's often important when we're thinking of protocols for testing Bell inequalities or doing various kinds of key distribution protocols and so on, that certain choices that are made by Alice and Bob and other participants, perhaps choosing a measurement basis and so on, the choices there should be made independently of what other agents in the protocol are doing. So again, we see a kind of natural idea of dependence and independence. An example of dependence would be that in teleportation, when Bob does the unitary correction, then this obviously should depend on the outcome of the measurement made by Alice. So we get both dependence and independence arising naturally. And we can think of dependence as indicating a form of information flow, and independence the absence of information flow. So another aspect of this sort of general theme of things that we've been discussing within this workshop. So this issue has been studied explicitly in logic for quite a long time. In particular, a classic discussion going back to the late 50s is the idea of the Henking quantifier. So the Henking quantifier is a basic kind of branching quantifier, as it's called, is where we have this kind of matrix where what we're trying to express is that for every x there exists a y. By the way, that's what Hodges says as his favourite theorem in logic. For every x there exists a y. Rather splendid result. But anyway, for every x there exists a y depending on the x, and for every u there exists a v depending on the u, but where there are no cross dependencies. The y doesn't depend on the u and the v doesn't depend on the x, and then such that some sort of further property holds. So Henkin had the idea of this quantifier, and if we think of the Skolem form, sort of standard idea of Skolemization, where we replace existentials by function symbols, which then get existentially quantified on the outside, then we can actually give an interpretation of this branching quantifier formula using this Skolemization. So the point is we have an f and a g. F is a function only of x but not of u. G is a function of u but not of x. Henkin asked the question whether this branching quantifier was something that could be expressed within first-order logic. And Ehrenfreund showed that it couldn't. And in fact, this is a very powerful construct that essentially takes you up to a system equivalent to a significant, well, the basic significant fragment of second-order logic, sigma 1,1. You see these existential function quantifiers on the outside. As a typical example of what we can express with a branching quantifier that we can't express in first-order logic, we have the property that two sets are equipotent. They have the same cardinality. So if we think of the predicates A and B as defining the two sets, here's the Henkin quantifier, and we say that, so we're really thinking of the Y as something functionally associated with the X, and of the V as something functionally associated with the U. So we're saying that we're mapping A's to B's by the first function, and B's to A's by the second. And essentially, if you perform the substitution with those Skolem functions, here we write y equals f of x, and v equals g of u, and you perform those substitutions through, then you see that that formula is exactly expressing that there's a bijection between the sets corresponding to the extensions of the predicates A and B. And in fact, the whole of sigma 1,1 can be expressed using these quantifiers. So this is much stronger than first-order logic. So I mean, just to make the point, in logic, one of the key dividing lines is between first order and what lies beyond, specifically second order. If you buy second-order logic with its standard model, then you've essentially bought a large part of set theory. Well, all of this got elevated into wider awareness with some interesting new ideas and twists by the work of Hintiker and Sandu, starting off in the late 80s, and then with this book by Hintiker with the not overly modest title, The Principles of Mathematics Revisited, which appeared about 10 years ago, with what they called information-friendly logic, IF logic, which has really become quite widely studied since then. And the basic idea is to generalize and at the same time introduce a kind of linear notation for this idea of expressing specifically the dependence of some construct or dependence of some choice on other things in the scope. So actually they introduced this rather strange slash notation. So for example, you have a quantifier for some x slash y, meaning there exists an x which must be chosen independently of y. And we have no idea what y is, and somehow it's sort of sitting there somewhere on the outside, but whatever it is, we're not depending on you. So that's what it's saying. And with that, we can write a linear version of the Henking quantifier. Okay. And even giving a sort of sensible syntactic account of these / quantifiers is not entirely obvious because of their outward-reaching scope. So I made an attempt to do this and to give a general compositional account of the syntax of branching quantifiers, of the semantics, game semantics of these things in a paper a couple of years ago. Now, it turns out that these kind of strange forms, although they may be interesting in themselves, aren't strictly necessary. And a nice simplification was introduced by Jouko Vaananen, well-known model theorist and set theorist, and developed extensively in his recent book on what he calls dependence logic. So the focus shifts from independence to dependence, and this turns out to make life simpler. And in particular, there's this nice idea that instead of having these exotic quantifiers, we concentrate the new idea into an atomic predicate, a dependence predicate, and the idea of this is that it's asserting that the variable x depends on and only on the variables listed before it. And then we can reduce so then we have a kind of backward slash version of the quantifier, which actually Hintiger had also introduced in another paper. So the backward slash says for some x depending on and only on x1 through xn, and that turns out to be a more manageable thing. And then that just turns into a guarded quantifier with this specific atomic formula of guard. Okay. But, of course, what does it all mean? Now, Hintiger has a whole story about what he calls game theoretical semantics, but it isn't very long on the games, really, and I would say that it largely reduces to talking about scholemizations, such as we have here. So, in the end, what a strategy for him means is something as specified by such a scholemization, and the point of the logic is to annotate which variables, which parameters the functions are allowed to depend on. And the focus is very much on the model theoretic content. So, although one can look at it from a sort of what we're perhaps more familiar with as a game semantical point of view, that's not really, in fact, where the focus of all this discussion has been. One of Hintiger's claims was that it wasn't possible to give a compositional semantics for independence-friendly logic. For some reason that I never understood, he seemed to be very proud of this fact. And instead, that one should give a game theoretical semantics, which is essentially this reduction to Scolen form that we've seen. So in a very nice piece of work about 10 years ago, the well-known model theorist Clifford Hodges showed that one could give a compositional account of the semantics. And Hintiger, being a philosopher, asserted the privilege of not accepting that the question had been answered. I don't think he ever has. But we're going to look at Hodges' work. And let's do this in two stages. Let's firstly recall the solution to an earlier problem, namely Tarski's well-known definition of truth in a structure. Phil, you may cover your eyes if you wish. I know that you associate with some people who don't like Tarski. But we remember that Tarski solved the problem in the sort of way that the sort of interesting solutions often are, by solving a more general problem. So, indeed, giving a compositional account of truth of sentences is not really possible to do, because sentences have constituent subformulas which are not themselves sentences. You open up a quantifier and you have something with three variables. So, and this is really something that's been enormously important for computer science denotational semantics and so on. Because what Tarski did, this goes all the way back to his classic paper about truth in formalized languages and so on, was to solve the problem of giving satisfaction of formulas that may contain free variables relative to an assignment of values to the free variables. So we have some first order structure with underlying set A. What he did was to deal with open formulas, and so this is how I'm going to write the satisfaction relation. We assume that all the free variables of phi are included in the set X. S is an assignment of elements of the structure to X, so what we would call an environment in denotational semantics. And M is the model, the structure, that also gives you interpretations of the relations and function symbols and so on. And then we have the familiar inductive definition that we all know, which for the quantifiers, notice, expands the environment by updating it. And then it has the usual Boolean conditions for the propositional connectives. And via Dana Scott, this idea came down into the absolutely standard use of environments of denotational semantics, but that's where it originated from. Now, Hodges' key idea in seeing what was needed to give a compositional semantics to this independence or dependence-friendly logic was to see that we could take over the Tarskian idea, but you have to lift up from satisfaction by single assignments to satisfaction by sets of assignments. Hodges actually called these sets of assignments trumps, and Van Allen calls them teams. So I'm going to follow Van Allen's terminology and call them teams, which I think is quite a good name. And what we're going to do is consider the semantics, the Hodges semantics. I mean, Van Allen is built on Hodges' work of dependence logic. So what we call dependence logic here will be formulas built up in negation normal form, so from atomic formulas of their negations, by conjunction, disjunction, and universal and existential computation. As we'll see, there's a bit of an issue with negation. There's always a sign there if you sort of work in negation normal form where things are easier to control. And we'll say that a team on X is now a set of Tarski assignments on the set of variables X. And corresponding to what we've already seen for single assignments, we need an idea of expanding a given team by making an assignment to a variable. There are actually going to be two operations that we need. The first one is given a team on a set X, given some variable V, then and given an element from our structure, then we expand the team by expanding simply by pointwise extending every assignment in the team. And on the other hand, given a function from the team into the underlying set of the structure, then we expand the variable by the function by updating, by, so to speak, expanding every assignment in the team by mapping the variable to its image under this function. So, two operations that we have on teams. So we should expect something new. I mean, the first one is just pointwise extension of the familiar one. The second one is less expected, but after all, something new has to be happening because we're making this abrupt transition from first order to some part of second order logic. And with that, we can give a satisfaction relation. Same kind of format as we saw for Tarski semantics, where we're really saying when a team satisfies a formula rather than a single assignment. And in practice, I'll drop the M. The M is always fixed in the background. It's our model solution. And firstly, for literals, atomic formulas of their negations, we just operate the Tarskian definition pointwise. We say that a team satisfies a literal if every Tarski assignment in the team has the standard definition of satisfying an atomic formula in an environment. You look up the relation in the structure, you map the variables to their values under the assignment, and you just see if that tuple of values is in the relation. And for negation, it's just the complement. And then the cases for now things start to get less familiar and expected when we come to the connectives and quantifiers. So the clause for conjunction is okay, but we see something curious in the disjunction. A team T satisfies a disjunction if there exists some teams U and V which decompose T, so T is the union of those, and U satisfies phi and V satisfies psi. So those is the conjunction there. And actually this is where we see that it's quite good to think of this team terminology. You have a team of assignments and they kind of split up, and for each one, each of them has to satisfy one of the disjuncts. So they kind of split up into two sub-teams, one of which are the teams that are going to satisfy the first disjunct, and the other is the team that satisfies the second.
But there's no requirement that they be disjoint, right?
No.
It's very much like a conjunction, though.
Yes, doesn't it? But that's the Hodges semantics of disjunction. And by the way, it's quite easy to show that in the case that we just have first order logic, I haven't dealt with the dependence predicate yet, but all of this boils down to a straightforward pointwise extension of the usual Tarskian semantics. So if we didn't have the dependent structure, we just have first order logic, so pointwise extension for atomic formulas and these clauses for the connectives and quantifiers, that the team satisfies a formula just if every assignment in the team, Tarski satisfies the formula. So even though we have a disjunction there, there's a conjunction in that clause, nevertheless there's a disjunction in the decomposition into a union. So each individual assignment gets, so to speak, to choose whether to verify the first or the second. Okay.
So the same, if phi and psi share the same variable, then T will contain two different assignments. Is that the idea?
No, actually we're assuming T is assignment on the set X, and U and V are taken to be assignments on the same set of variables. No, it's just to do with truth conditions. An ordinary single assignment satisfies a disjunction if it satisfies one of the disjuncts. If you have a team of these things, and you want all of them to satisfy the disjunction, well, some of them are going to do so by virtue of satisfying the first, some by virtue of satisfying the second, and actually some may satisfy both, but that does no harm.
So, yeah, okay, so I see. So if for example, psi is actually false,
yes,
then you're going to redirect all your team to...
Of course, you could have that U is T and V is empty, or whatever. Yeah, absolutely. And then for the quantifiers, we use our two updating operations. Actually, I didn't quite give the right, and that's why I was hesitating over this update. What I mean by T with V substituted by A is pointwise, putting in all possible values from the structure for the variable pointwise into the T. So that's what that means. Should I write that down, or is that clear?
What is A?
A is the underlying set of the structure.
Okay.
Just the underlying set of the structure. We're keeping that structure fixed for our discussion. Okay? So that's how the connectives and quantifiers look. This is all a bit simpler than what Hodges did, because Hodges was always interpreting these weird quantifiers. Here we've just extracted the basic interpretation of quantifiers, and we only have to deal with the dependent separately as an atomic formula. Another complication in IF logic, and Hodges was at great pains, sort of trying to convince Hintiker. Hodges was at great pains to follow faithfully every little twist and turn of IF logic, some of which are quite idiosyncratic. For example, in their enthusiasm for information friendliness, not only did they have information-friendly quantifiers, but they also had information-friendly conjunctions and disjunctions, which, for various reasons, doesn't actually work that well, and a useful part of that could be encoded with quantifiers, so I'm not bothering with that. Okay, and then, and I should mention that again, sort of with the attempt to sort of exactly track what IF logic looked like. So strictly speaking, this is the positive part of the definition as given by Hodges and Varner. Because there's also a negative part which defines satisfaction for phi as for the positive definition, but with respect to the De Morgan dual of the formula. So exchanging conjunctions and disjunctions and universals and existentials. And the point about giving two independent definitions like that is that you can then have a game theoretic negation where you interchange the two satisfaction relations. But frankly, I don't see much point in that. We may just as well work in negation or... I mean, what that let them do was only have disjunction and existential quantification, for example, but this negation. I think it's simpler just to have all these connectives and write them out like this ones. Okay. So that's exactly what Hodges wrote down with the aim of sort of capturing what Hintikka was doing, and proved that it did, of course, and that it was and actually taking over the term from computer scientist, he actually proved a full abstraction result for this semantics. Okay, so now we have to give the semantics of the dependence predicate, because otherwise we're just with first order logic. As I say, it's a simple result to prove that without the dependence predicate, all we're doing is pointwise lifting the task of semantics. And the point about the dependence predicate shows very clearly why we really need to consider sets of assignments, because dependence is not a property of a single assignment, but it's like a coherence property of multiple assignments. So a couple of notations: an equivalence relation on assignments modulo some subset of the variables, just if the two assignments agree on the variables in that subset. And it's also useful to have an idea of a function from assignments into the underlying set, depending only on the variables in W, which I write with a subscript W notation, if it factors through a projection onto that subtuple. Of course, that's a surjective map, so if such a factorization exists, it's unique. And now we can define the semantics of the dependence predicate in a sort of coherence relation type of form. We say that a team satisfies the dependence predicate if for every pair of assignments in the team, if they agree on the variables in W, then they give you the same value on the component of V. And if you think of the assignments, I mean, you can think of them as tuples, rather like in a database where the fields are named by the variables, then this is exactly expressing functional dependence as a database theory. And you can see that it's meaningless to speak about one tuple and whether you have a functional dependence there. But when you have multiple tuples, then it makes sense. And we can give an equivalent definition using this other notation, which makes the functional dependence more explicit, that we satisfy the dependence assertion if there's a function from the team into the underlying set which depends only on the components in W, such that the V component of every assignment in the team is that function of the W components. Okay. So that's how the semantics is done. Now,
there's in probability theory you use a sub-sigma algebra to talk about those dependencies, or the lattice dependencies.
Yes.
So I don't know if that's maybe I don't know where you're heading, but if there is some quantum thing and probabilities later on.
Yes.
You're not going to tell us now, okay?
No, there aren't going to be probabilities, but I mean I agree that would be an interesting point. So I think actually there are possibilities for that, looking at that kind of thing, but that's not where we're heading on this occasion. So anyway, the theory, once we get this semantics, then the sort of theory of it is developed extensively in Varnadin's book. Lots of connections with second order logic and set theory and so on. But I think there are a lot of very basic questions that remain. They certainly remain from Varnadin's point of view. I was interested to discuss them when I went over there for a visit recently and had some nice discussions. Well, from my point of view, the basic question is what on earth is going on? Where does this construction come from? Is it canonical in any way? Why does it work? And what structures are really at play here? And from his point of view, of course, we know that this is, in the standard interpretation, this is equivalent, the dependence logic is equivalent to sigma 1 part of second order logic. There's no hope of a complete axiomatization. But on the other hand, we might hope to get a useful completeness theorem if we allow a larger class of models. So that's one sort of thing that would be useful for this study. And another point is to look for representation theories. So if we have a larger class of models, when do we really get back to the intended ones? So, with that in mind, let's look at this structure again. And in terms of sort of different cultural aspects of logic in its diverse forms, and there's kind of super good model theorists here, but there's a lot of things that they are not necessarily aware of. So we already had some classics of categorical logic recalled in this workshop, so let's recall another one, Morvier's Adjointness in Foundations from '69, which had the idea of the hyperdoctrine. And in the first instance, we can use it to reorganize the Tarski definition into a nice categorical structure.
Morvier would stand up shooting like reorganizing Tarski by the hyperdoctrine.
Yes. Well, probably if he was going to shoot me, he would already have done it. So, but you never know. Okay, so we form a base category with objects, just the Cartesian powers of our underlying set. And arrows are set theoretic functions. This allows the first order terms, so in the usual way then we can interpret first order terms of our language and tuples of terms as functions. So we're terms in variables, so we come from a tuple of objects that tell us, well, they're just assignments on the variables. And then composition of functions models substitution of terms. This is really Lorvier algebraic theories down in the base category. And then above each of these objects in the base category, above each a to the n, we're going to have a meaning for propositions on that, given by a functor, which maps each object to a Boolean algebra of propositions. And the specific one that we're thinking of here, so we're going to think of a to the n just as another way of thinking about assignments, say conventionally from the first n variables into a. And we're simply going to assign the power set of that as our set of propositions, which are going to be meanings of formulas in those free variables. And of course, we're going to think of that as the meaning of a proposition of a formula in free variables as being the set of assignments that satisfy that formula. And we can think of this as a contravariant functor from our underlying category, which gives us the meaning of our elements, into the category of Boolean algebras. So, of course, each power set is a Boolean algebra, much more than that. The Boolean algebra structure allows the propositional connectives to be interpreted, and each Henry relation symbol of our language is interpreted as an element in this power set. And it's the contravariant power set functor, and that will carry substitutions through in the appropriate way. And then we have Lorvier's fundamental observation, which really adds something to the picture. It's not just a reorganization, it's and also a generalization, but it really adds something. Adds something that basically good logicians apparently don't know. I mean, I was somewhat astonished by this. But quantifiers are adjoints. So let's just recall this. Consider a function. So we've said we're working with the contravariant power set functor, so we're taking inverse image, map subsets back to subsets. Any such function will have both a left adjoint and a right adjoint. And in the important case for the sort of usual interpretation of logic, the function we're taking is going to be the projection function, because we're quantifying a lot of variable. And then the right adjoint to this projection function will be the universal killing the variable, the universal quantification, and the left adjoint will be the existential quantification. So in terms of what's going on here, we have a to the n plus 1 going to an by some projection. So the projection under inverse image pulls back tuples here to all the tuples such that omitting the one coordinate gets you there. And this has both a left adjoint and a right adjoint. I remember to get my junctions the right way up, so let me see. This is the left adjoint. No, remember, this is the for all, isn't it? This is the exist. So you see that these have the right types. They are both killer variable. They take us from propositions over a bunch of variables of x to propositions just over a bunch of variables without x. They're both killer variable. And all the sort of proof theoretic properties of the quantifier are encapsulated in this junction property. Okay, and of course, we have hyperdoctrines in general. This immediately generalizes. So we have the base category with finite products, a contravariant functor from that category into Boolean algebras for classical logic. Quantifiers are defined then as the adjoints to the projections as above. And there are certain naturality conditions guaranteeing correct behavior under substitution, often variously referred to as Beck-Chevalley or Frobenius reciprocity. And predicates are interpreted as elements of the appropriate fibers, as we already said, and this extends to cover equality. And of course, we can also vary this scheme to, so for example, instead of Boolean algebras, we can have Heiting algebras, and then we get models of intuitionistic predicate logic. And things like the completeness theorem and so on can all be put in a nice conceptual form in this general setting. Okay, so having recalled all this, however much not in the spirit of those who originated it, the question is, can we achieve the Hodges construction as a functorial construction on hyperdoctrines? Or at least that's the way I would like to pose the question. And actually a very basic question is, we saw that sort of not completely familiar looking semantics of quantifiers with sets of assignments. So a very natural question is, in his semantics, are the quantifiers indeed adjoints? Do we have the same kind of description of the quantifiers? And the key clue is the observation made both by Hodges and Vanneman that the sets of teams that satisfy any given formula in the logic are always downwards closed under subsets. Hodges remarks that for sort of general reasons, this is going to be the only simple property that's an invariant of these sets because of the connections with second-order logic. If you think about the downwards well, I mean, we can sort of go back to the definition. It'd be a simple matter to verify that all those conditions were downwards closed. And in fact, they both work exclusively with the downwards closed sets of teams in dealing with whether it's with IF logic or dependence logic. Vanneman does consider a sort of what he calls team logic, which is the Boolean closure of dependence logic, where you throw in complement that we did not have, and of course that destroys downward closure. But in many ways, it's a less elegant system. I think it's basically the wrong system, and the dependence logic is the right one. I think he actually feels the same way. So now let's recall a simple general construction. Let's start from a commutative ordered monoid. Then the set of lower sets, so it's an ordered monoid, of course the monoid is monotone with respect to the order. Then the set of lower sets of M ordered by inclusion is the free commutative quantile generated by this ordered monoid. And it's the object part of the left adjoint to the obvious forgetful functor. And of course, as a commutative quantile, it's a model of intuitionistic linear logic. It's a version of phase semantics. Usually in phase semantics for linear logic, one does not have a partial order on the monoid. You just take the power set. But having an order does no harm and everything works nicely. To make the tensor product, we take the down closure of the pointwise sets of additions of elements to downwards closed sets. And we have the familiar definition for the linear implication, which is always downwards closed, given that A and B are. And there's an observation, which I'm not sure is all that helpful in our context, but there's a nice paper by Harry Simmons and Bill Mitchell, which says that under various conditions this construction gives you a model of classical linear logic. One of those conditions, so they have conditions involving ordered abelian groups. But one of the conditions is actually when the monoid is a Boolean algebra. And of course, from our point of view, what we have in mind is the situation that we've just seen, where we started with a set, for example, a to the n, and we went to this power set. So, of course, we can think of this, well, it's got almost all the structure you can imagine, but in particular, it's as a semi-lattice, it's a Boolean with respect to the union, which was the interesting operation if you think of our definition of disjunction. So, under union with empty set, it's a semi-lattice, and of course, it's then a Boolean algebra with respect to complementation. And as Mitchell and Simmons observe, in the case that your ordered commutative monoid is that special case of being a Boolean algebra, you get a negation that works straight on, without any closure under facts, by the way, where you define the linear negation in terms of this combination of complement and non-membership. And if you work it out, if A is down-closed, so is not A. Having said that, I find what this means completely incomprehensible, and I don't propose to use it, but nevertheless it's there. And one may also note that modulo this issue of down closure, which actually in the semi-lattice case goes away, the A tensor B is exactly the way we define the semantics of disjunction in the Hodges semantics. So if it looked familiar, it was. It's really an instance of a linear conjunction. So indeed, it looked like a conjunction, and really, in these terms, it is a conjunction, even though it was interpreting disjunction in that semantics. And we've also acquired a new connective, namely linear implication. Okay, so with that general idea, we're going to sort of interpret the Hodges construction as a functor, or an instance, I should say, of a functor, which carries classical hyperdoctrines to some other kind of hyperdoctrines. So we're still going to discuss a bit which logic we should end up in. And the functor is just going to be by composition with this downwards closure functor that we've just seen. So given the hyperdoctrine P, going into Boolean algebra, say, we construct a functor by composing with this down closure. Notice that this is an order-enriched functor, as one easily sees. So the Boolean algebras are order-enriched category. The L functor is downwards closed, is order-enriched, so it preserves adjoints. And the first since it preserves adjoints, and we had in our original classical hyperdoctrine the quantifiers described as adjoints, then applying this functor to them will give us adjoints again in the new category. And what we can observe, so therefore that must be the canonical interpretation of the quantifiers in the new lifted interpretation, the down-closed sets, the Hodges construction interpretation. There's nothing else for them to be. And then it's simply a matter of checking, as one easily does, that Hodges definitions are exactly giving you the image of the Tarskian interpretation under this functor. So that mystery is completely dispelled. They're the only thing they could possibly be. And therefore we can answer that the Hodges quantifiers are indeed adjoints to the image under L of substitution, the image of the projection functions. Now, of course, this thing, L of M, carries a great deal of structure. It's a completely distributive lattice and so on. And it carries more than the structure of a quantile. It's also a complete Heiting algebra and carries an interpretation of intuitionistic logic in a straightforward fashion. And here are the relevant clauses. So we see here a conjunction that really looks like a conjunction, and a disjunction that really looks like a disjunction, and the familiar Kripke-style definition of an intuitionistic implication, which of course is giving us the adjoint to the conjunction. And here it's downwards closed set, so we're thinking of extension of our knowledge by going downwards in the order. So we're saying for all n refining n, if n satisfies A, then n satisfies B. That's the condition for n to satisfy the intuitionistic implication. So the conjunction is the one we had previously. The disjunction is new and the intuitionistic implication. Now, the situation where we have both intuitionistic logic with its own implication and multiplicative linear logic both existing in the same setting is exactly the situation where we can interpret the logic of bunched implications, BI logic, introduced by Pim and O'Hearn a few years ago, which in turn forms the basis of separation logic as introduced by and developed by Reynolds and O'Hearn, which has become quite widely used in influential logic for verification in recent years. So now my little joke in my title is all explained. Because what I'm going to suggest is that the appropriate propositional logic to take, really for dependence logic, should be this logic of bunched implication. Not just for the sake of it, but because it's actually going to give us an interesting logical perspective on the ideas about dependence that are motivated by it. Now, concretely, in terms of the team semantics, which is just a particular case of this general situation, we can give the clauses for all these propositional connectives. And we see that the linear conjunction, or the multiplicative conjunction, has exactly the definition we saw earlier, so it is a conjunction now in this version. Here we have the linear implication, and here we have the intuitionistic implication. And it's really the intuitionistic implication and other intuitionistic connectives and the linear conjunction that I think are the interesting connectives in this logic. In fact, another guise for this L construction is as the free construction of BI algebras, the algebras for bunched implication, as quantiles are to linear logic, or Heiting algebras are for intuitionistic logic, over ordered commutative monomers. Okay, and of course we also need to know that this structure is preserved. And in fact, it's the case that whenever we started with an interpretation of a term in our base category, if our original hyperdoctrine interpretation was, so it's going between ordered sets, so it makes sense to ask whether it's a right adjoint. And of course, that's true for the inverse image. Well, there's the direct image. Right? Then applying these lower construction to it preserves intuitionistic implication and multiplicative conjunction, and hence is a morphism of these propositional algebras for the logic of bunched implication. Okay, so the proposal is that this is really the right logic to understand what's going on, and now we want to see how we can use it to understand dependence a bit better. So let's try to break, dependence predicates already introduced to simplify the study of these information-friendly quantifiers, and now let's try to analyze dependence in a final way. So consider the following predicate. So C for constant, I suppose. So a unary predicate which holds in a team, and again it only makes sense in a team if for any pair of assignments in the team they have the same value at the variable v. So in other words, it's saying the team is constant, has a constant value at that variable, it's single valued at that variable. And then you see that the dependence predicate can now be defined in terms of the C predicate. And this is the intuitionistic implication. If you think about the definition we gave earlier, so here we're thinking about this being true, so it means for every subset which satisfies the conjunction over here, then in other words, which is single valued on all the VI's, then it has to be single valued on V. So it's another way of expressing functional dependence, but it's been internalized into the logic using, interestingly, the intuitionistic implication. So it's kind of extending a binary coherence to the general case. And something that a classic in the literature of functional dependence are the Armstrong axioms, which are a complete axiomatization of functional dependence, and which therefore are sort of also discussed in connection with dependence logic, and sort of as a complete axiomatization of the dependence predicate in isolation. Of course, the interesting thing is how they interact with other stuff. But at any rate, if we look at these, in these terms, it all starts to make very good sense indeed, because if we translate dependence into these Horn clauses using the C predicate as we have there, then these are all translate into very familiar axioms of intuitionistic but not classical implication and conjunction. In fact, this is the usual identity axiom, A implies A. This is the C combinator, A implies B implies A, implies dear, I've got this, I need to look in like this. C implies B implies A. So in other words, a reordering or commutativity thing, which corresponds in fact to the exchange rule. So that's the second one. The third one is the W combinator, which is contraction. The fourth one is weakening, the K combinator, and the fifth one is the B combinator, which is transitivity of implication. And this is a well-known complete axiomatization of intuitionistic implication, just as it's a functionally complete set of combinators, but notice it's not an axiomatization of classical implication. Okay, and then just to kind of finish up with something towards kind of results that we're aiming at. So we can then consider how to, I think a good illustration of the different natures of the multiplicative and intuitionistic connectives is to consider something like the diagram of a model of this logic. So we have a particular model with a universe A, introduce a constant for each element of the universe, and then we can take all the true atomic sentences in the usual fashion involving these constants that we've introduced, and then the fact that everything is denoted by one of these constants is this axiom here that involves a possibly infinitary version of the multiplicative conjunction. You see, think of a team. You have an arbitrary team of assignments, so it could be assigning all sorts of things to V, but whatever it assigns, it has to assign one of these constants. That's what this is saying. So this is saying that's the whole universe is what's denoted by the constants. On the other hand, we can actually define the C predicate using the intuitionistic disjunction. And therefore we can define the dependence predicate. Remember the intuitionistic disjunction is where you have to put all your eggs in one basket. Your whole team has to satisfy one of the disjuncts. So the only way this can happen is indeed if we have a single value for the variable V in the team. And from that we can, well, semantically that will be a correct description of the C predicate, and hence our description of the dependence predicate. Okay. And really these things suggest the ingredients that are needed for a suitable representation theory. Okay, so really that's it. I don't want to sort of go on for too long. So basically the technical program then is to get a class of models, and we can see how the class of models will go. I mean, either just models for a BI predicate logic or an extension with axioms for the C predicate, such as we've just seen, if we want to get a stronger kind of result. But of course then it would be an infinitary logic, and we know that this is unavoidable because of the kind of second order nature of the standard semantics. So on the one hand we can get a completeness theorem, and on the other hand we can recover set theoretic models. And what we're looking for actually are sort of as a variation of the usual kind of duality of complete atomic Boolean algebras and so on. We have a kind of two-layer structure, and what we're looking for are things that are prime atoms. Prime with respect to the tensor product, and atomic with respect to the intuitionistic disjunction. And there's essentially a suitable kind of Stone duality and representation theorem that can be extracted from these things. And hopefully soon will be forthcoming paper with Yoko Banana on this. Okay, so that was a little story about dependence and separation. So that kind of brings me to the end. So just before I finish, it's been a great few days as far as I've been concerned. We've seen lots of pictures, so as a brief kaleidoscopic swirl through some of the pictures that we've seen. We saw how to beat a grandmaster in chess, of course, executed in icing sugar and other media as well. We saw how proofs could be represented geometrically, and how this same representation led to dynamics of cut-in animation. With a very minor change of perspective, we saw that we were in the realm of diagram algebras, as used in representation theory and in topology, in particular in the Temperley-Lieb algebra, its connections with knot theory and so on. We saw that with the same ideas we could express functional computation as diagrammatic simplification. So there's the B combinator. And the same kind of things showed up in quantum information. We could trace information flow path through entangled quantum systems, and this could be axiomatized in a categorical setting with the same kind of structures that we've seen for these other ingredients. We heard some of the latest developments in the preceding talks today. I finished where I started there. I just want to finish up by saying it's been a great few days as far as I'm concerned. The hope was to bring people from different backgrounds and interests together, and that they would interact, and it's really, as far as I'm concerned, succeeded beyond my expectations. So it's been great to have the company of all of you over these few days, and thank you all very much.
Are there comments or questions? People are just going out. Well, I have to say, Samson, that I promised a wide range on Wednesday when we started this, with the hope that there would be this kind of interaction, and I have to say it's been amazing sitting here watching all this unfold. It's really been special, so I want to thank you. Having watched these lectures for many years now, I said we started in 1984. I've never seen one that encompassed the breadth and range of topics, or a breadth and range of topics like this one did, in such a coherent way. In fact, most of them are fairly narrowly focused. So this is really a special one that I think will go down as a particularly important event in the history of the Clifford lectures. So thank you very much for accepting the invitation and for helping me. And thank to all the speakers, some of whom are absent. But thank you very much from the department. It's been a pleasure having you here.
Let us thank the organizer.
As they say in German, gern geschehen.
Thank you very much, Mike.
You're welcome. Anytime.
Yes?